All right, moving on in electrochemistry. Today we're going to talk a little bit about how E and G and K are all combined and used together. So first thing I want to do is to just remind you in terms of what it means to be spontaneous. We said, you know, there's a couple conditions that are true, that delta G has to be negative in order for it to be spontaneous. K kind of naturally has to be greater than 1 in order to be spontaneous. I mean, certainly that's going to allow us to be moving towards the products. And another thing that you may have found as you were working on the battery is this E0 value, which is essentially a voltage that we're able to achieve through a battery, for example, which is a spontaneous reaction. And in a battery, the E0 value needs to be a positive number. So these are three conditions that all are true when a reaction is spontaneous. Now E0, as you may recall, gave you, like in the battery, a unit of volts. And so something that is going to come into play today is that you should know that a volt is a joule per coulomb. So what that means is a joule, of course, is energy, and coulomb is a unit of charge. So just kind of something to keep in mind as we move forward. All right, what we're going to do is a couple of standard conditions equations. We talked about standard conditions when we were talking about free energy, and so we're going to continue to elaborate on that as we talk about voltage and how that is also going to play a role. So remember, standard conditions is referring to 1 molar for solutions and 1 atmosphere partial pressures for gases. All right, 3 equations that you should know. First one is new, and it's relating spontaneity, or Gibbs free energy, to kind of electrical work. And that equation is that delta G0 is equal to negative N F, yes, that's kind of a weird fancy E, Faradays constant, E0. So here's what these values mean. This is sort of a electrical work kind of scenario. N refers to the number of moles of electrons that are transferred, and that's from the balanced equation. I'll show you an example of that. F is Faraday's constant, and Faraday's constant, which is, I believe, given on the useless information sheet, so I think you should check, 96,500 coulombs per mole, and that's really per mole of electrons. So it's a unit of basically how much charge you get per mole of electrons is what that's telling you. E0 is the standard voltage. And so this is the voltage of, say, you can think of a battery most simply, where the solutions are in standard conditions like 1 molar. And again, if you want to see how those units work out, these volts are joules per coulomb. And so when you kind of look at all those different units, what you're going to end up with for delta G is units of joules. All right, so that's one equation. Second equation, I'm just writing it down, but you already know this one. Delta G is equal to negative RT natural log K. And I'm going to show you in a moment why I'm writing that down. Okay, number 3. Now, if what we do here is we take a look at, in rearranging kind of equation 1 and equation 2 and putting them together, we get this equation. E0 is equal to RT over NF natural log K. All right, so you might want to think about what that unit for R is. It's not liters atmosphere, so this is going to be the 8.314 joules per mole Kelvin version. Temperature, of course, needs to be in Kelvin. Still the number of moles of electrons transferred, still the number of coulombs per mole of electron, and then natural log K. So this is an equation that can be useful to us as well. Here's why this becomes kind of helpful. I'm going to draw this little triangle here. These are the 3 equations that can allow us to kind of move around between KEQ, between standard voltage, and between Gibbs free energy. Because if you have one of those, you can figure out either one of the other 2. So we've already done this one here, KEQ and delta G. You can use the equation delta G is equal to negative RT natural log K to move between delta G and KEQ. The first equation that I gave you helps you go between delta G and E naught, and that's delta G naught is equal to negative NF E naught. So if you have one, you can get to the other. And the third equation is from going from E naught to KEQ, and that's E naught is equal to RT over NF natural log K. So this little triangle here allows us, if you have one of those constants, to figure out the other. Now I'm going to make a point because on your useless information sheet, I'm pretty sure this equation is given, but they give a couple others that are related, and they're very specific to 25 degrees Celsius. And your useless information sheet also tends to use log base 10 instead of natural log. So its kind of rearranged version is, log K is equal to N E naught over 0.0592. You might wonder, well, how is that related? So here's what they did. If you take this equation and you plug in 25 degrees in Kelvin, so 298 Kelvin here, you plug in the 8.314 and you plug in Faraday's constant and you convert the natural log into a log base 10, that ends up being this 0.0592. So it ends up being E naught is equal to 0.0592 over N log base 10 K. So this is an equation if you have the equilibrium constant and you want E naught and you're at 25 degrees Celsius, you could use this equation. Check your useless information sheet, you guys. Make sure that what you need is on there, because some are on there, most are on there, but you should kind of become familiar. So let's do a quick kind of problem to go along with some of these equations. So I'm going to draw a battery up here. Let's say we got a piece of copper in a copper ion solution, but it's going to be at standard conditions, so 1 molar copper ion. And piece of silver in a 1 molar silver ion solution. We've got a wire connecting, we've got a salt bridge between them. And as we look at this, first of all, you can check if you think your battery stuff, you can take a look at the values, knowing that in order for this battery to work, E naught has to be a positive number. What we're going to do, catch up. See, it's just like in class. We're going to calculate E naught, delta G, and K. So when I look on my standard voltage chart, it's in your text, and we're going to assume that the temperature is 25 degrees Celsius here. If I want to calculate E naught, turns out that copper ion is going to be oxidized, and this is the voltage I get off the chart. And silver ion, and I'm doubling this here, I probably shouldn't double it to start with. Let me show it to you. When you look off the chart, it's 0.80 volts. I know I had to reverse this one, because if I would have reversed this one, my voltage would have been a negative number, and I need it to be positive in order for this battery to work. So I reversed this one compared to how it was written on the chart. I'm pretty sure your chart is in reduction. But to balance this out, since 2 electrons are lost, I need 2 electrons gained. But I do not multiply that voltage value. So what I do is I end up with 0.46 volts is my E naught value. And I can, of course, write the balanced equation that goes along with it. I didn't ask for it, but I'm just writing it for the sake of what's going on there. All right, once I know delta E, now I can compute the others. So I know that delta G naught is equal to negative NF E naught. Here, 2 moles of electrons are transferred. I know that because of this. There are 2 moles of electrons being transferred. So I can plug that in, 2 moles. Faraday's constant, 96,500. Now I'm going to change the units on you here. This is normally coulombs per mole. A volt is a joule per coulomb. A coulomb is a joule volt. And so if I plug that in here for coulombs, I'm going to get joule per mole volt. I'm doing it to help my units work out because my E value is in volts. And when I do that, I get negative 89,000 joules. Because moles cancel, volts cancel, I'm left with joules. So this is my delta G value. And then if I want my K value, once I know delta G is equal to negative RT natural log K. Plug in my delta G value. Oh, sorry, that was a not. Negative 89,000 joules is equal to, this is the 8.31 version. I want it in joules, so it cancels. Times my temperature, 298 Kelvin, natural log K. Solve for K. K is equal to 4.3 times 10 to the 15th. And then if I just want to bring it back full circle, I could use this equation. And plug my numbers in. RT over F, and this one, check, might be on your useless information sheet. Actually, don't even worry about it. 8.31 joules per mole Kelvin. This is the 298 Kelvin. This is the 96,500. When you simplify that, it becomes 0.0257. You don't have to memorize it. 2 moles of electrons, natural log my K value. And what I get is E naught is equal to 0.46 volts, which is just brought me back full circle. So just wanted to show you how you can use those to go back and forth. All right. Last thing I want to show then to kind of wrap this up is something called the Nernst equation. So I'm going to show you this battery because here's the thing. Sometimes we aren't at standard conditions. So if you recall this equation back when we were doing Gibbs free energy, we had this equation when we were not at standard conditions for delta G. We could use an adjustment. Well, now we know that delta G is equal to negative NFE. So if we plug that in, negative NFE, notice this is not E naught because I'm not at standard conditions, is equal to negative NFE naught for that delta G plus RT natural log Q. If I divide to get rid of this NF and just solve for E, what we get is E for our cell, that's our battery for example, is equal to E naught minus RT over NF natural log Q. That is the Nernst equation. Yeah, that just kind of sounds funny. But the Nernst equation is used when you want to find E not at standard conditions. You know, you don't want 1 molar solutions in your beaker, or as soon as the battery runs, they're not 1 molar anyway. So let's think back to our battery and the one I just did before. I'll just kind of redraw this picture. You know, as this battery ran, here's our 1 molar copper ion, here's my piece of silver, and my 1 molar silver ion and salt bridge and wires and all of that stuff at 25 degrees. And the equation, which was this, which is going to be important to us, that as the battery runs, what we can see is that this silver ion concentration is going to go down. It's going to get used up. And the copper ion concentration is going to go up. It's going to be producing more as the reaction runs. So let's try to figure out what the voltage of this would be at a different point. All right, so if I was going to write a KEQ, and these actually are, you know, equilibrium reactions. That's what happens when a battery is dead. It actually reaches equilibrium. It doesn't actually die. The KEQ is going to be the concentration of the copper ion over the concentration of the silver ion squared. The solids don't go in. So let's write a little ice table. And here's our silver ion that we start with, and our copper ion we start with. Let's say we start with 1 molar solutions, like we did. Well, let's say we let it run until half of the silver ion is used up. Then we're going to make a quarter more. Why? Because it's 2 to 1 over here, right? And so we end up with 0.5 molar silver ion left and 1.25 molar copper ion. Well, if we want to find out, well, what is the voltage that we should get from that, we can plug it into the Nernst equation. E naught was 0.46 volts. We already did that one. Minus, I'm going to use the at 25 degrees, so we're going to assume we're at 25 degrees here. So I'll use the version that's on your useless information sheet. 0.0592 divided by still 2 moles of electrons. Log, now Q is plug these numbers into this equation. So log of 1.25, made that bracket too big, sorry, over 0.5 squared. And when we do that, we end up with 0.44 volts. So you can see that the battery now doesn't have as much voltage it can give. And honestly, you consider a battery dead when the voltage just isn't enough to run your cell phone, your iPod, your whatever. It probably is never going to actually be dead. It won't run to zero. At some point, this voltage drops off enough that your electronic equipment just doesn't use it. So that finishes up the Nernst equation. Have a good one, you guys.